Chapter 4 is all about the graphs of the circular function. So if you've taken a pre-calc class before, you have seen what sine, cosine, and tangent look like. We're going to jump into the beginning of them. The goals of these lessons is to be able to talk about the different attributes of the sine and cosine, eventually tangent function and their reciprocals, and then graph them. But what we are talking about in general is a periodic function. Since we know that the unit circle repeats itself as you go around revolutions of the circle, we can see that these functions are going to do something similar. So just like this EKG of a heartbeat, the blub blub of your heart, glub, lug, glub. Is anybody in health sciences? What's the actual words I'm supposed to use there? It's like glub, glub and lub, which are the sounds your hearts make. Glub, lub. Anyway, it's not important, but this is going to repeat over and over again. That is a periodic function. So what we're learning about is these functions that repeat themselves over and over again. So here's the technical definition of a periodic function. A periodic function is a function such that f of x is equal to f of x when you shift it a little bit to the left and right. So we are multiplying by some value, some integer, and what's called the period of the function, which is how long it takes for it to repeat itself. For every real number x in the domain, every integer n, and some positive number p, the least possible positive value of p is called the period of the function. We are basically saying we can define periodic functions to be things that repeat themselves. So if we look at the very top of this like heart monitor boop, boop thing, right here, we have a certain distance until we get to the same height, correct? And if we repeat that same distance, keep going, we're always going to be at the same part of the function each time we repeat that horizontal distance. That makes this a periodic function, that these just repeat over and over again. Since we know a few things, we actually know a lot about periodic functions. The circumference of the unit circle is 2 pi. So the least value of p for which sine and cosine functions repeat themselves is going to be 2 pi. Every 2 pi units, we will repeat ourselves because we are back at the same value all around our unit circle, each revolution. Therefore, sine and cosine functions are periodic functions with a period of 2 pi. For every positive integer x, sine of x is equal to sine of x plus 2 pi times n, which means every revolution after that. Or cosine of x is equal to itself every revolution around the circle. They're going to repeat the values, which is honestly how we were able to do a lot of our work in chapter 2 with the revolutions around the circle. It's the same concept, but now we're going to put it into a graph and not just units themselves. Here's what the graph of sine looks like. It is related to the unit circle. The domain consists of all real numbers corresponding to angle measures. So our input value is angles on the unit circle. Its range corresponds to the y-coordinates or sine values on the unit circle, which means it is ranging from -1 to 1. Because if we think about it, sine represents vertical displacement. The lowest the graph is going to go is -1, and the highest it goes on my unit circle is +1. Now, we're going to graph just one period of this function, and I've kind of given you the values here already. We know this from our unit circle, but right now, just because we're sketching this, I want you to gently mark off, don't aggressively mark off, all of the values that are not like perfect halves or ones or zeros, just because we're not going to graph that correctly. In fact, this is approximately 0.707, and this one is approximately 0.866. There's no way we would graph that accurately, so we're going to ignore those two coordinate points right now, although they are important for an actual graph. We're sketching this right now. But let's plot these points. So first things first, we have 0, 0. Because at angle 0, the sine of 0 is 0. Pi over 6, the sine of pi over 6 is 1/2, so we're going to put a little dot at 1/2. And then if we skip all the way down to pi over 2, pi over 2 comma 1 is a coordinate point for the sine function. And then we're going to skip a bunch. We go to pi comma 0, so at an input value of pi, my output is 0, which makes sense. At 0, or at pi, we're at a height of 0. At 3 pi over 2, we're back down to -1, and then at 2 pi, we reach back around our unit circle, and our vertical displacement is 0. So if we look at this and we connect the dots, this is one period of the sine function. Let me do that again. I did not graph it very well. Tell me some things you notice about this. Don't use fancy math language. What do you notice?
They go up and then down.
Perfect. It goes up and then down. That's a periodic function, and it's going to continue to repeat itself outside this one period from 0 to 2 pi. It's going to oscillate back and forth, bouncing basically between -1 and 1 for forever. It is continuous over its entire domain, and the domain of a sine function is all real numbers from -infinity to infinity. Its x-intercepts have x values of the form 0 plus pi times n, where n is an integer, meaning at 0, we have a 0. Add pi to it, we have a 0. Add pi to it, we have a 0. Add pi to it, add pi to it, add pi to it. Every single one of those values is a 0 of the sine function. The period of the sine function, just like the unit circle, is 2 pi. The graph is symmetric with respect to the origin. If I were to graph more of it this direction, like into the negatives, you'd see that it could spin on top of itself. So the function is an odd function, which then means that if we had the sine of some negative value x, it'd be equal to the negative value of sine of x. This all has to do with the unit circle, the ASTC quadrants. This is exactly verifying all of that. So we know a lot of things about sine. We're just putting them into a graph now. This visual right here just shows you that we are mapping the vertical displacement. It's way better in color than it is just looking at it. But if you notice, at 0, our vertical displacement is 0. At pi over 6, our vertical displacement is a half. And at pi over 2, our vertical displacement is 1. Then we start getting closer to the x-axis, so my vertical displacement goes down. We get further from the x-axis, but in the negative sphere down here, and then come back up, which is how we get the shape of the sine function. Eventually, we will do cosine, aka we're going to wait till after lunch because I know y'all are just thinking about food right now. Yeah. We have like 30 seconds till the bell rings for lunch, and we'll come back to talk about cosine after lunch. Lunch, we were talking about the graph of the sine function, and it would have been a nice segue to the graph of the cosine function, but it has been 30 minutes because of lunch. Let's talk about the cosine function. It is also related to the unit circle, but cosine represents the horizontal displacement of the graph, or the x values around the coordinate, around the unit circle. Its domain consists of real numbers, again corresponding to angle measures around the unit circle. Its range is this time the x coordinates, or cosine values on the unit circle, which again, because horizontally we go from -1 to 1 on the unit circle, that's going to be the range of the cosine value, cosine function. We're going to do the same thing to graph this function that we did before. Again, we're going to ignore these values that aren't nice and pretty since this is a sketch for us. They are values that are plotted, but since we're humans, we're not going to be able to plot 0.866 or 0.707 accurately. Otherwise, let's do what we can. At angle 0, the horizontal displacement is 1 because we are fully to the right of the unit circle. When we get to pi over 3, we are at 1/2, so we are halfway back towards the y-axis. At pi over 2, that's when we are on the y-axis, so our horizontal displacement is 0. At pi, we are fully to the left of the unit circle, so that's -1. At 3 pi over 2, we're back to 0, and at 2 pi, we make it back up to that maximum value of 1, because that's a horizontal displacement on the right. When we play connect the dots here, it kind of looks like the shape, because last time we unofficially said that the sine function goes up, then down, then up. Doesn't this still go down, then up? And if we kept going, we'd say down, then up, and down, then up. They are exactly the same shapes, except shifted to the left and the right of each other. So we talk about that is a really not my best curve for that function, but you get it. The graph is continuous over the domain from -infinity to infinity. The x-intercepts this time, since the first one begins at pi over 2, it's going to be pi over 2 plus pi times n, because every pi units we cross the x-axis again. The period of the cosine function is still 2 pi. The graph is symmetric with respect to the y-axis this time, because we could fold it along the y-axis and the left side would look exactly like the right side, which means that the function is even. Therefore, any negative input value would be the same as the positive input value. And that again is because the quadrants where cosine is positive is A and C. So the S and T quadrants, it would be negative. That's your reflections horizontally. But if we go ahead and look at this, I'm going to color code this, and if you followed my color scheme, I'm using the same one. This dashed line is representing sine. So it's the one that starts at 0, then goes up, down, up. That's going to be sine. Maybe we want to write that down so we can see it. The blue one here, which is blue on my screen, but I will re-emphasize that it is blue, that is cosine. This is the one that starts at the maximum value, goes down to the minimum, then back to the maximum, crossing those center lines, instead of starting at the center line. But if you notice, these shapes are practically the same. It's just that one has been shifted to the side. So we say that the graph of the cosine function, that's the blue guy, the graph of the cosine function is the graph of the sine function that has been shifted to the left by pi over 2 units. So if we take this sine graph and shift it to the left, those points would all be in the same spot. This point would be here. This point would be here. Every single important value on the sine function you can force to be a cosine function, if you shift it by pi over 2. Which means every sine function and cosine function are going to look very, very similar. It comes down to where you start graphing them. And in fact, where you start graphing them is very, very important. Sine is always going to start at the center line. For the parent function, that means we're starting at a 0. When we start to shift this vertically, we're going to shift the center line. I don't think we're doing that today. The cosine function is always going to start on its maximum. And by starting, I mean that's your y-intercept. So if we look at this graph, both of these points right here are the y-axis, are on the y-axis. So we're either going to start on our center line, or a 0 for the parent function, or at a maximum, but then the pattern for either of them is the same. I'm going to use the word center instead of 0, but if we go center, then we'll go maximum, center, minimum, center, max, center, min. We're graphing sine. The pattern is the same, but the starting point is different. Max, center, min, center, max, center, min. Same pattern, same graphs, just shifts of each other. So the goal of today, once we've started to see these functions, is to talk about different attributes of them when we start to change the parent function. We're going to start transforming this in different ways. The first way we're going to transform these graphs is by changing what's called the amplitude. Now, I will be recommending that you follow my color scheme on this, because this is the color scheme I'm going to use for this entire unit. Amplitude is going to be pink. The amplitude of a periodic function is half the difference between the maximum and minimum values. It describes the height of the graph both above and below a horizontal line passing through the middle of the graph. If you ever do sound waves, this the crest and the trough are the words you'd use for that. So it's measuring the crest from the center to the top, or this trough, center to the bottom. We have this formula for amplitude. It is max minus min divided by 2. It's the difference between the maximum and minimum values, half of it. Bless you. The graph of a sine of x or a cosine of x, where a is not 0, will have the same shape as the graph of the parent functions, except that their range has been extended. So we're going to have numbers multiplied in front of either sine or cosine that are going to change our maximum and minimum values. One of them will be positive, one of them will be negative, but the amplitude itself is always positive because it's an absolute value. If you see a negative in front of a function, that just means it's been reflected instead of changing the amplitude to something negative. It's helpful to think about that. So let's see what this might do. We're going to graph y equal to 2 sine of x on the interval from negative 2x to 2x. 2 pi to 2 pi, whatever. And then compare the graph to the parent function. The parent function is already here. However, we're graphing double of that. So we're going to take every output and we're going to multiply them by 2. So let's do this slowly. What is the output at this coordinate point? No, not input, sorry, output. 0. What is 0 times 2? 0. Still 0. Okay, great. We got another coordinate point right here. What is the output when the input is negative 3 pi over 2? 1. So if I multiply that by 2, where should my new output be? 2. If we keep this pattern going, 0 times 2 is 2. Negative 1 times, what? 0 times 2 is 0. Let me say that correctly. Negative 1 times 2 is negative 2. Do you notice what's happening here?
Yeah, it's getting like longer and longer.
Let's use the word stretched, maybe? It's getting stretched. In fact, it is being vertically stretched by a factor of how much? 2. These are vocabulary words we'd heard before when we did transformations in Chapter 2 of college algebra. We're just applying them to sinusoidal functions, which means we're calling it an amplitude now. So just to reiterate that, this is a vertical stretch or dilation by a factor of 2. The new range of this function is no longer from negative 1 to 1. It's from negative 2 to 2 because we're multiplying by that amplitude. We're stretching the graph up, taking the crests and the troughs and stretching them vertically. Easy? Yes?
Should be.
Multiply all of the outputs by whatever number is there. We can also change the period of the function. So the amplitude changed the vertical stretch, making it wider or like taller or like, what's not taller? Shorter. Forgot the word there for shorter. We can also change the period of the function. We're going to use blue for the period. We can think of the graph of y equals sine of bx. Notice this time we're multiplying on the inside of the function. In fact, I'm going to put parentheses around this guy to begin with because it might be more helpful as we're learning. That is multiplied on the inside. Inside transformations are always horizontal, but this b times x is a horizontal stretch of the graph. And when b is between 0 and 1, and it is a horizontal shrink when b is greater than 1. Horizontal, inside, and opposite. So small numbers on the inside, small numbers on the inside cause this to stretch horizontally, and big numbers on the inside cause it to shrink horizontally. So again, we have these two functions that this looks like a copy paste because it really is. The rules are the same for both sines and cosines. Whether we are multiplying this inside of a sine or inside of a cosine, either way, it will change the period of the function, specifically by a factor of 2 pi over b. That will be the new period of these functions when we are changing the period. 2 pi divided by whatever number is there in your sine and cosine function. So let's see. It says we're going to graph y equals to cosine of 2x on the interval from negative 2 to 2 and compare that to cosine of x. Well, cosine of x is already graphed for you. What number do we have multiplied here on the inside? 2. So if we're going to redraw this and change the period, what we would do is we'd fill in that formula we have right above here, that the period is equal to 2 pi divided by b, which means we're doing 2 pi divided by 2. The 2's cancel. The period of my new function should be pi, which means I should finish the entire shape between 0 and pi. Right now on my graph, we're finishing the entire shape between 0 and 2 pi. So I need to make this like faster. Faster is the wrong word. We're going to call it higher frequency. So now, a shorter period. Now we need to finish the whole thing going from maximum to maximum in pi units. So I need to go all the way down and up, not between 0 and 2 pi, but between 0 and pi. Which means I will have more waves in each little section. This is a higher frequency graph. We have taken it and horizontally shrunk it, making the waves appear more often. It is a shorter period, higher frequency.
The bottom one's at 2?
No, it should be at 1. I just drew that real bad. Let me draw that again while I'm not also speaking at the same time. I can like also actually give myself coordinate points here. I know, confusing because I'm using the same colors here, but blue was cosine for us. Now, if we're going to use old transformation vocabulary here, we would have said it's squished in like this. I'm doing my hands towards each other, yes? Am I horizontally or vertically changing my hands? Horizontally, which means this is now a horizontal dilation. Changing the period is a horizontal dilation. In this case, it's a horizontal shrink because it got faster. This is by a factor of 1/2. It's the reciprocal. Horizontal, inside, opposite. You flip that number over. Its range is still the same, though we didn't change the range at all. We changed the period. Multiplying a number on the outside changes the range and the amplitude. Multiplying a number on the inside changes the period and the frequency. So let's talk about how to actually graph these things. Your book does a very interesting process for graphing it, but it's very straightforward. So we're going to follow the process from the textbook. And we're going to graph in 5 steps. It's really 4 steps because step 5 is connect the dots. Step number 1, you're going to find the period of the function. So you're going to look at the formula that it gives you and figure out what b is. And then decide the actual period of this function, 2 pi divided by that number. Then you're going to go to your x-axis and you're going to lay off a distance of 2 pi over b, whatever that is. Meaning you're going to put a tick mark at the very end and label it whatever your period is. That means lay off the distance. You're going to then divide that distance into 4 equal parts. How many equal parts? 4 equal parts, okay? In regular pre-cal, we called that the x increment. In AP pre-cal, we did not use that terminology, but that's the x increment. We're going to evaluate the function for each of the 5 x values resulting from step 2. I know it says 4 parts, but include 0. That's the 5th value. The points will then be your maximums, minimums, and your center lines or x-intercepts. We'll go ahead and do those in... I don't want to even do them in green. We're going to do them in regular colors. Okay. Then step 4, we'll plot the points found in step 3 and join them with a sinusoidal curve having the amplitude absolute value of A. We're double checking that we have the right amplitude here. And draw the graph over an additional period as needed. Okay. Here's our first one we're graphing. We're graphing -2 sine of 3x over 1 period using those guidelines. Because this has a number multiplied on the inside, the period of this function is going to be 2 pi divided by 3. Once I know 2 pi divided by 3, I'm going to go to the end of my axes and I'm going to label that coordinate point 2 pi over 3 on the x-axis. Boom, boom. That's what step 1 is telling me to do. We found the period and laid off that distance. We also want to find the amplitude. What's the amplitude of this graph? 2. What is that negative going to do? It's going to flip your maxes and mins. So we're going to put 2 comma reflected so that we remember to switch our pattern. Every max becomes a min, every min becomes a max. I also am going to figure out the 4 intervals, the 4 equal parts between 0 and 2 pi over 3. If this is in the middle of 0 and 2 pi over 3, how far is that? Halfway between 0 and 2 pi over 3. Pi over 3. Why is it pi over 3? What's half of 2 pi over 3? Pi over 3. Get rid of the 2. Because pi over 3 plus pi over 3 is 2 pi's over 3. So we just want one of them. You half that number to get the center. Now we're going to half it again. What is half of pi over 3? Pi over 6. So this one that's halfway between 0 and 0 and pi over 3 is pi over 6. Now I'm going to walk away from my iPad and do this real fast.
Okay.
This interval is pi over 6.
Mm-hmm.
What's pi over 6 plus pi over 6?
Pi
over 6 plus pi over 6. 2 pi over 6. What does that reduce to?
Oh.
Great. So this is 1 pi over 6, 2 pi over 6,
3 pi over 6.
3 pi over 6 is that last missing one. But of course, 3 pi over 6 reduces. What does 3 pi over 6 reduce to?
Pi over 2.
Pi over 2. You are finding the x coordinates of the x increments, meaning halfway between 0 and 2 pi over 3, we're going to label pi over 3. Halfway in between those, we're going to do pi over 6. 1 pi over 6, 2 pi over 6, 3 pi over 6, but we know 3 pi over 6 reduces to pi over 2. Okay, now we need to work from the insides out, because this function wants me to multiply these values by 3. What is 0 times 3?
0.
What is pi over 6 times 3? Oh no, our fraction rules. Pi over 2, because it's 3 pi over 6, and we reduce that down to pi over 2. What is pi over 3 times 3 pi? Pi. What is pi over 2 times 3? 3 pi over 2. What is 2 pi over 3 times 3? 2 pi. What do you notice about the numbers on the second row? Well, true. You should also recognize those values.
Oh yeah, that's the and then yeah.
They're the quadrantial angles. They should be the quadrantial angles if you're doing this right. Should. Because the quadrantial angles are the easiest ones to know the sign of. What is the sign of 0?
Oh, that's the listen.
This might be a good time to have your unit circle on your desk. What is the sign of pi over 2? 1. What is the sign of pi?
1/2.
That one's 0. What's the sign of 3 pi over 2? And what's the sign of 2 pi?
0.
0. The quadrantial angles are easy to know the signs of. You're thinking of the 4 quadrants. Now, if you look at this table, it just says to take what we have up here, sine of 3x, and multiply it by negative 2. What's 0 times negative 2?
0.
What's 1 times negative 2? And then,
0.
great, we have our amplitude worked in now. So if I do this on my graph, here's 1, here's 2, here's negative 1, here's negative 2, I'm going to follow this pattern. My table says input 0, output 0. My table says input pi over 6, output negative 2. Input of pi over 3, output of 0. Input of pi over 2, output of 2. And then back to 0. If you already know the pattern for sines and cosines, you know this is reflected. It goes center, min, center, max, center. If we kept going, we'd repeat that pattern. So you start with the period, divide it by 4, which you can do half, half, and triple, which is what we did. Then you can fill out the table. Can we try one more before we ask a ton of questions?
Do we have a choice?
No.
Oh.
Great. The title of this example is wrong. I forgot to edit this. It should say cosine right here, but it doesn't mess up the actual problem, just the title. We're going to graph negative 3 cosine of pi x over one period using the guidelines from above. So question,
Answer.
what is the period of this function?
3 pi? No, 3.
What's the period of a normal cosine function?
Is it
2 pi.
Yeah.
And what is our b value here?
That's pi.
It's pi. So our period is going to be 2 pi over pi, but like
Oh, so
it's 2.
Mm.
So we're going to lay off that distance. Here's the value, the distance 2. What's going to be the amplitude of this function?
3.
3. And is it reflected?
Yes.
Okay. So we should make sure our pattern, I spelled that wrong. We should make sure our pattern reflects that. Okay. In my table, the first thing I fill out is the furthest x value. We know that one's 2. Then I went to the middle. For this one, what would be the middle number?
1.
And then I filled out in the next middle between 0 and 1. What is that? 1/2. And so what's that missing box? 3 over 2. Very good. Now, following the rules on my table, it says to multiply the number above it by pi. 0 times pi is 0. Pi times 1/2 is pi over 2. Pi times 1 is pi. Then 3 pi over 2. And then 2 pi. Oh, snap, it's your quadrantial angles again.
What?
Easy peasy. We're going to take the cosine of those things. What's the cosine of 0?
0.
No.
Oh.
1. What's the cosine of pi over 2? 0. What's the cosine of pi? Cosine of 3 pi over 2?
Something.
0. And then 1. But we are multiplying these values by -3 for a change in the amplitude, which means my actual output values will be -3, 0, 3, 0, and -3. So we can graph this. We know that we are going to have input values at those 4 values from the top of my paper, from the top of the chart. 4 equal parts between 0 and 2. We know also that our amplitude is going to get up to 3 and down to -3, and we can start our pattern. This is cosine, so it says 0, -3, and then 1/2 0, 1 3, 3/2 0, and 2 -3. If you know the pattern from your pre-cal class before, this is max, center, max, center, min, but we've reflected it, so we're starting at a min, center, max, center, min. It's the same pattern you learned in those courses before. We're just building a table to show why. That's a thing. We can also give you a graph and ask you to write the equation of it. So you're looking for the period and the amplitude. So if we see here, it says to determine an equation of the form y equals a cosine of bx or y equals a sine of bx, where b is greater than 0 for the given graph. We need to make 3 choices here. While you can write every sine as a cosine and every cosine as a sine, we're only going to answer one here. And I'm going to tell you right now, we would choose to write this form for this problem. Why would we choose cosine over sine for this problem?
Because it do like a little woo.
Okay, be more specific because they all do that shape sound that you just made, but
It goes down, up, and then down again. It doesn't have like a little extra.
yes, I think what you're trying to say is what Angel just said. Say it again. It starts at a minimum.
Yeah.
If you're starting at a minimum or a maximum, you're starting with a cosine function. Normally it's maximum. Obviously this one's minimum, and so it's reflected. If you would start at a center line, that's when it would be sine. Okay, a couple more things we need to see here. We need to know the amplitude of this graph. Amplitude is a formula that we have. The amplitude will be found by doing the max minus the min divided by 2. What's the maximum of this graph? Sorry, the maximum? 2. And what's the minimum? And we're going to divide that by 2. Ooh, minus a minus, gross. What is minus a minus? So 2 minus -2 is 4. 4 divided by 2 is 2. My amplitude is going to be 2. The last thing I need is the period. If I look at this graph, how long does it take for this function to start and stop one wave? 4 pi. So if I'm looking for b, I know that the period is 4 pi. I also know that the period is 2 pi divided by b. I got to figure out what b is. How would you solve that equation for b? Oof.
Wouldn't you multiply 2 pi by 4?
We would multiply both sides by b first. So we end up with 4 pi b equal to 2 pi. Like I'm getting the b out of the denominator. And now if I wanted b by itself, I think I heard somebody say it. Divide by 4 pi. So b is going to be equal to 2 pi over 4 pi. So it's just 1/2. All we needed was 3 things. To choose between sine and cosine, we've done that. To find the number we'll plug in for a, we've done that. To find the number we'll plug in for b, we've done that. This means that this answer is going to be y equals to 2 cosine of 1/2 x. You plug the a where the a goes and the b where the b goes. Oh, but I totally messed up. What have I forgotten here? The reflection. What should be in the very, very front of this?
Negative.
That was a true mess up. That wasn't me trying to see if you were paying attention. Oops. Happy Monday.
Happy Monday.
When we're working with trig functions from real life scenarios, like example 7, they're not going to give you nice, neat numbers like I did on the first 2 examples. So we're going to need to use a calculator to help us find these values. Example 7 says the average temperature in degrees Fahrenheit at Mould Bay, Canada, I think that's how you say that. I haven't Googled it, so probably, can be approximated by the function f of x equal to 34 times the sine of pi over 6 times x minus 4.3, where x is the month and x equal to 1 corresponds to January. 2 is February. It will be a phase shift. We'll talk about it later. To observe the graph over a 2-year interval, we're going to graph the window between 0 and 25 on the x-axis and negative 45 and 45 on the y-axis. This is something you may not have done before unless you took my AP Pre-Calc class last year. So on your calculator, first of all, make sure you're in radian mode, which if you reset your calculator, you are. We're going to go to y equals, we're going to type in that equation, 34 sine of pi over 6, open parentheses, x minus 4.3, close parentheses, close parentheses. It is pi over 6, yes. I'm taking it straight off of here. Okay. Now if we press graph right now, it doesn't really show us important information because first of all, I don't even think you'd see most of the graph. This has an amplitude of 34 and usually we just see from 10 to 10. So when you do periodic functions, you're going to press this button right here you might have always politely ignored called window. The window tells you what you're going to see on your graph. This is like the zoom button on Desmos where you start to move it from side to side just like haphazardly. This is you choosing the window to see. Our problem wants us to see the first 2 years, so we're going to go from 0 to 25. Since our months are counting by every x value, like that's 2 years and an extra month. And then our y value, it told us to look between negative 45 and 45. So it must be that our maximum and minimum temperatures lie between 45 degrees, negative 45 degrees Fahrenheit and 45 degrees Fahrenheit. It's cold in Canada. Moving on. If we graph this, here's what 2 years of temperature models would give you in this place in Canada. So what we're going to do on our notes right here is we are going to sketch that so we could see what we did. This is here-ish. Do your best.
Define best.
Mine are better. Then we can answer some questions. The question here wants me to list the period and the amplitude. So question, let's start with the easy one. What's the amplitude here? 34. Super easy. 34 is in front of sine, so 34 is my amplitude. Easy peasy. The period is also relatively easy. We need to take the number that's multiplied on the inside. That's pi over 6. And we're going to fill in our formula for period, which is 2 pi over b, pi over 6. Ooh, yuck. We're dividing by a fraction. What's the rules?
Keep, change, flip.
Ah, amazing. Keep, change, flip.
So pi's cancel out, it would be 2 times 6.
Now, does that make sense? What are we modeling here?
Temperature.
And doesn't temperature repeat like practically every year?
Pretty much.
12 months.
Yay.
That is our period here. That makes sense. We're modeling temperature over a year. Makes sense. Then we can keep going. Now, especially because we have this in our calculator. I almost say computer. Calculator. According to this model, what is the average temperature during the month of May? Well, we can really figure this out. What month is representing May? 5. So if we want to say, what is the output when the input is 5? I'm really just trying to figure out where this graph is when the input is 5. So we're going to do what the little box says. We're going to go to trace, and we're going to type in 5 and press enter.
Oh.
It moves the turtle for you.
Oh.
I want accurate answers here, so don't just try to move the turtle yourself because you'll get decimals that I don't want. I want exactly what happens when x is equal to 5.
What is it actually called?
I don't know. I've always called it the turtle, and I've never asked.
12.18?
Yeah, 12.18 degrees Fahrenheit.
Should we do that where it says C instead of above?
It's B.
No, it's B.
Wait,
Oh,
wait,
see, this is
so
a
are
completely
we
different
putting
question.
12.18451 or just 12.18?
Totally depends on how the question asks you the round.
How are you writing it?
I've put 12.18.
How are you writing? Are you putting Y
I
or?
was about to do 5 instead of F.
It's Y or it's f of 5 because that's my outputs. So it says what would be an approximation for the average annual temperature at Mold Bay? What does it mean to do an average?
Add everything and divided by how, the frequency,
Let's work smarter, not harder. If this is an extreme value right here,
yeah,
and this is another extreme value,
yeah,
are these opposites of each other?
yeah,
So they like cancel out, right?
yeah,
What about this one? Would it have an opposite value right here?
yeah,
What about this one? Would it have an opposite value?
yeah.
Okay, so if all of these are gonna like cancel each other out, what is the average annual temperature in this city?
It's a great question.
0?
It's 0.
Oh.
This average annual temperature is going to be 0 degrees. Next class, we're going to learn that that's called the midline of the function or the center line of the function. It's the average. It's our zeros. This just happens to also be 0.
Doesn't it also change?
It can also change if you change the displacement of the graph. A
But
vertical
we're not gonna-
we will do that vertical transformation. Not today.